Hi everyone, welcome to this episode of Keipert Labs. Today we're going to finish off our mini-series on Newton's laws of motion, focusing on the Newton's third law. Okay, so far we've looked at the first law, which we can summarize with the concept of inertia, that an object will have the tendency to maintain its state of motion unless acted upon by an unbalanced force. And so it will stay stationary or it will stay moving at constant velocity unless a force is going to either speed it up, slow it down, or change its direction. And then Newton's second law we summarized with the maths equation of F equals ma, or as we kind of preferred to write it, acceleration of an object is equal to the force over the mass, net force divided by mass. So saying that when we apply an unbalanced force, how will that change an object's motion? And then in this video, we're going to address Newton's third law, often known as, or shortened as, action-reaction. Okay, so that's where we're going to focus our energy now. Okay, so in terms of how we would word Newton's third law, here's kind of the phrase that we would use, which may sound very familiar to you. And here we have it. For every action, there is an equal and opposite reaction. So it's a phrase that's quite a familiar sort of scientific phrase, but you may not have actually been able to put it in context before, or think about what it actually was relating to, but we're thinking about it in terms of forces. And so what we can kind of summarize it or add to it is this idea that forces work in pairs. Okay, so there's our big kind of concept. And so what I mean, in order to kind of elaborate on that a little bit, I'm going to give you a bit of an example here. Okay, so let's think about a chair. Okay, and then we have a person sitting on that chair. Okay, happy as Larry. Happy because the chair is holding them up. Okay, what we have here in this situation is a situation where we have equal and opposite reaction and two forces that are at work here. Okay, so what we know that there is gravity on this person when they sit on this chair. Okay, so there is a force of gravity going down this way. Okay, so gravity. And that's pulling them towards the center of the Earth. And in fact, accelerating them towards the center of the Earth because of Newton's second law. There's an acceleration because of the force that's on them. But what we know is that this person is sitting still because there's a second force on them. And that second force is pushing them up. So the chair is putting a second force on them, and this chair that's pointing up. And we call that, I can't remember if I've introduced this terminology to you before, but if not, the idea of a normal force. Now, it's not normal in terms of the everyday, the typical, that sort of the word of the use of the word normal, but normal as in perpendicular to a surface. Like, so it's perpendicular to what the chair, the bottom of the chair here. And so what happens is that the reason that this person doesn't crash through to the floor and doesn't kind of get pushed into outer space is that these two forces are equal. Okay, so what we have is that these forces are the same type. Okay, so push or pull, twist. Okay, so in this case, we're talking push forces, same type, same magnitude, that is, the size of the force is equal, but in opposite directions. Okay, so the same type of force, in this case we've got a push, so that as he pushes down on the chair because of gravity, the chair pushes up on him with the same amount of force. Okay, the same type, the magnitude is the same. Okay, so I've drawn my arrows the same length to reflect that as well, but the idea that the chair pushes up on him with the same amount of force that he pushes down on it, and it's opposite in direction. Okay, one is up and the other is down. Okay, if you're talking sideways, one is left, one is right. Okay, if one is southwest, the other's northeast, or depending if you want to give it more specific direction. Okay, because in this situation we have forces working in pairs. Okay, there's two forces involved in this scenario. Okay, and now one of the things that can be tricky about Newton's third law is that often it can be hard for us to appreciate that there are more than one force working in a given situation. Okay, like, so if let's say you have a brick wall. Okay, so this is a brick wall, and then you, as a person who loves physics and wants to test out these ideas, decides to, with your scrawny stick person arms, push on the brick wall. Okay, so you're pushing on the wall. Okay, that's the arrow indicating your push force. And but the idea is that with the same amount of force you put on the wall pushes back on you. Okay, you experience that in the way that you feel that in your hand, and especially if you push really hard on the wall is going to push really hard on you, and you might get hurt. Okay, like if you take a crash tackle into it, you'll experience this rather abruptly, shall we say. Okay, but so the idea, so it's the same sort of thing. So we've got the same type, the same magnitude. Okay, so the harder you push on the wall, the harder the wall will push on you, but we have opposite in direction. But now it's easy in this sort of a scenario to see that you're pushing on the wall. Okay, you can recognize that you're making an active choice to make that happen because you love physics. But you don't always appreciate the way that the wall is pushing back on you. Okay, because you feel the texture of your hand, but it's hard to recognize that. And that can be the challenge with Newton's third law, is recognizing when you get a pair of forces happening. Okay, and so let me give you a kind of a final example, just to try and an everyday sort of thing to try and help clear this up for you. Okay, so let's say you have a table, and let's say you have a book on that table. Okay, so gravity is meaning that this book is trying to move towards the center of the earth, so it's putting a force on the table that's proportional to or relates to how much mass that book has. So light book, small force; heavy book, big force. Okay, and then the table is pushing up on the book with the same type of force, in this case a push, the same magnitude, so the size of the force is the same, but the direction is opposite. Okay, now we don't really notice how this is kind of working, because we can't always see the changes that are happening in the table and the book as a result of that pushing together. But you'd notice it if the table wasn't working, and all of a sudden if it cracked and it fell through, or you tried to put a safe or some like an anvil or something, Bugs Bunny style, on this table, that you would notice the difference, that the table all of a sudden can't give that much force back, and it cracks, it breaks under the force. Okay, so what we can see is Newton's third law happens in lots of situations. Okay, one of the follow-up things you're going to do now, we're going to watch a video of some astronauts on the International Space Station demonstrating the principles of Newton's third law in a situation where you can notice it much more clearly. Okay, so hopefully, given you a couple of scenarios, help to outline a few things to help clear this up for you. All right, thanks very much for watching. Bye for now.